All right, so this has to go good. We did ester preparation yesterday, and you're going to do the ester lab. Well, you would do it tomorrow, but I said no, I'm not going to be here. So you're going to do it on Friday. Yeah. Today? No, but we have a lab on it tomorrow. I mean Friday. You're going to do that exact same. You're going to make 5 esters back there. So I'm going to do things a little out of order. I'm going to do the reactions of the esters today. Okay? Reactions. And I'll finish those up pretty quickly. One of them is really, actually not that quick. I just realized something. The last one we're going to do, we have another lab next week on. So we have actually a preparation of an ester lab. That's Friday. And then we have a reaction of an ester lab. That's going to be probably Monday or Tuesday of next week. So next one on your sheet, though, is conversion into alcohol carboxylic acids. Do you recognize this reaction?
Yes.
What is it?
It's the reverse of that other one.
Exactly. It's just the reverse of the one I gave you yesterday. In the preparation of an ester, you took a carboxylic acid and an alcohol, and you made an ester and water. Okay, now, today, I'm not going to do it. I'm not even going to do an example of this. If you simply take your ester, and by the way, if you notice, there is I think I drew an arrow like that on yours, or no? Something like that. It should be. It should be a double-headed arrow. It should be 2 ways, because this reaction is reversible. Okay. All right, so I'm not going to do an example of that one, since it would just be the exact opposite of what we just did yesterday. However, this is a different one, so let's do an example of this one. Have room for an example on that one?
No.
No?
No.
Oh, okay. Well, that's because I'm going to spend more time on the other one, I suppose. But reduction into alcohols, what you do there is you take your ester and you turn him into 2 different alcohols. And I really should have an example there, but basically, let's do a real short one. If I had a really easy ester like this one. All right? Okay, so what ester would that guy be?
Oh, methyl.
Methyl, because that's the part that came from the alcohol.
Ethyl.
Ethanoate. So this guy would be methyl ethanoate. If I took him and I added hydrogen in the presence of copper oxide and pressure and heat, I would get what 2 alcohols, do you think? Yeah, ethanol and methanol. And that's all you would do. So you would have to write down ethanol for that guy and methanol for that guy. All right. So the difference here is, this is important, it's one little word different, one little letter difference. This ester plus H2 versus this ester plus H2O. If it's plus water, it's just the reverse of your carboxylic acid and alcohol reaction. You're going to make your carboxylic acid and alcohol back. But if it's hydrogen you're adding to it, you're going to get 2 alcohols. You're not going to get a carboxylic acid from that. Okay? So you have to look carefully at those. Many people get those mixed up. All right. Those are the 2 normal reactions you would see on a worksheet. Now, the big one we're going to do a lab on. Okay? This is kind of a neat one. And that is called saponification. Okay? Or soap making. Yes, we're going to make, and you're going to get to take the soap home. All right? A lot of the labs we do in Chem 2, if you haven't noticed already, are better than the ones we did in Chem 1. They're longer. They're more complicated. But the actual product you're making here is usually something useful. Tomorrow you're going to see, or Friday for you guys, you're going to see, alcohol, for example. But on Friday you're going to see the esters are going to be 5 very familiar smells. Very, very familiar to use in the cosmetic industry and in flavoring gums and artificial flavorings, artificial scents for perfumes. If you look on a lotion or it ends in ATE, it's probably an ester. And OATE is how you end the esters. And that's what gives a lot of these things their particular smell, their scent. All right? Well, saponification is another neat one. It has no smell. Soap doesn't really have a smell if you just use regular ivory soap without perfume in it. But I'm going to show you how to make it, and you're going to make it. You're going to take it home tomorrow. Okay? Soap is formed from the reaction of a fat or oil with a strong base. So copy that down. Now, some of you may be saying, I thought you said this was under this is number 3 in your notes under ester reaction. I thought this was an ester reaction. Why don't you say it's a reaction of a strong base with an ester? Because, this is something I never said before, fats and oils are esters. They're not short esters that have characteristic smells. They're big ones. They've got like 17, 20 carbons in them. All right? And I'm going to show you an example of that, which you're going to draw down below under the formation of a fat. So this formation of, one more thing to say here. Fats and oils are esters of glycerol and large organic acids. So that's why this falls underneath reactions of an ester. A fat or an oil is an ester. I told you that ester linkage, that way to hook 2 longer chains together, is actually used in living things all the time. One of the things it's used for is making fats or oils, storing energy, storing those carbons in the form of a longer chain of fats and oils for to be broken down possibly in the future for energy use. All right. So I'm going to show you 2 reactions. You can look at your paper there. You can see that there's this reaction here, the formation of the fat. That would actually fall if I were to have put it somewhere, which I didn't want to because I'm not going to ask it on a test. That would have fallen under preparation of an ester. Okay, so you've got that one. That's what we're going to do now. Then under here, I've got this one already filled in for you, where you actually take your fat or oil and you react it with sodium hydroxide. That's what you'll do next week. You will make soap, and after it cures and dries, and we're going to put it in molds, like different shaped molds, and you can take it home. It should be ready in about a month or so.
Can we use it?
I would not use it. I would use it for decoration only.
Oh.
Why? Because you don't mix the stuff together very well. Sometimes it does separate out too much. It's not done professionally, and your soap will end up being, a lot of times, your soap in particular will be very basic. And that means it would burn your eyes. And if you use it a lot on your skin, it would dry it out. All right, it probably isn't going to kill you. All right, but if you got it in your eyes, it's going to be way more irritating than just getting ivory soap in your eyes, okay, or Irish Spring. All right, so let's write this first formation of a fat down. This is actually how the ester, the fat or oil, is formed. You would take, and we've seen this guy before. We've actually used him 3 times this year. Glycerol.
Is this our only example?
Yeah, it is. This
Okay.
is what it is. This falls underneath formation of a fat. Okay? This falls underneath formation of a fat. That's where your notes are, formation of a fat. That big empty space is where you have to write that.
Okay, this one.
Okay? We've seen glycerol before. I used glycerol and I added potassium permanganate to it, right? And I oxidized it. And that's the guy that caught on fire in the fume hood, burned with that purple flame. Remember?
Yeah.
Okay. I also used them once before to help me make a soap bubble. Stay together where we caught that on fire for the burning of the propane, or actually it was natural gas, methane. And we're going to use it on Monday or Tuesday, whatever day I think we have a double on Monday, right? Yep. We'll probably do it on Monday. We're going to use it there to make our, actually, we're not going to use the glycerol. We're going to use the product of the glycerol to make our soap. Okay? So you take glycerol if you wanted to make your actual fat or oil. You react him with, look at that. This is a huge carbon compound. 17 carbons, 35 hydrogens. And you do this in multiple places. So that's, why this guy's a little different than your average ester. It happens in 3 spots. It happens at every place you have an OH is where you're going to hook these guys together. And I hope you can all see this, right? Let me use this little box around here, right? You can see that? You don't have to draw that box in, but you can see what's happening with that box. What are you going to split off when those guys react? No, use your head, guys. Not hydrogens. Not hydrogens, not oxygens. What do you think is going to be split off over here? What's going to form on your side for each one of those? Water. Yeah. HOH, HOH, HOH. You've seen this happen now. Dehydration kind of reactions. Multiple times. Got to start seeing it. Okay? You don't just, let's just get rid of an H for no reason, an OH for no reason. What's going to happen over here? I'm going to get water. All right, that's where the water is going to come from. And that's exactly what happens. Done this before with the regular, normal one-step ester reaction. You take an alcohol and a carboxylic acid. Let's do that. Okay? If you cover this part up, just look here. Stop writing for a second. If I didn't have the bottom half of this, okay, if this was not here, it's just not there, it'd be like methanol plus, and this guy was just, he wasn't there either, plus methanoic acid would give me methyl methanoate. Okay? Well, you're just doing, this is not just one carbon, it's 17 carbons long, and you're doing it at 3 different places on that glycerol molecule. And that's why you're going to get all these guys coming together to make that, which is called glycerol tristearate. Glycerol tristearate is a fat. And of course, you also get water. And how many waters will you get? 3, because you split 3 waters off over here. Right there, and right there. Okay? This is how you make your fat or oil. And the only difference between a fat and an oil, in general, is a fat is usually a solid and oil is usually a liquid, because a fat usually has more saturated carbons in here without double bonds, and the oil usually has more unsaturated ones that have more double bonds. And therefore, the oil will be more likely to be a liquid at room temperature than a solid. So butter, lard, animal fat, that'll probably be more saturated fats. Vegetable oil, canola oil, peanut oil, that would probably be more of these carbons would be double bonded instead of single bonds, more unsaturated, maybe shorter a little bit, and so they don't hold together as well. Don't have as strong aromatic forces. All right. There's your fat. Your fat, or your glycerol tristearate, is basically your ester. He's your ester. That is not soap making. That's how your body or other things make, or we can make, if we wanted to, a saturated fat, or a fat or an oil. Now, if we take this, which I'm going to redraw a little bit differently in my bottom part, which you already have. Luckily, this will take you less time to do because you're going to, you already have it drawn for you down there, right? If you take this guy right here, and all I did, if I'm not mistaken, is replace this big thing here with an R. You see now, look down below. Y'all looking down below in your papers? See how that's just an R there. That's the only difference between that. Okay? Everybody good with that? All right. All right, I'm going to go to that one now and show it to you. There he is. There's your glycerol tristearate, your fat or oil, basically your ester, reacting him with what? Well, that's what you're going to do on Monday. We're going to add our most famous base, sodium hydroxide. You don't have to use sodium hydroxide. You can use other ones. Our most famous base, though, we're going to make a solution of it. We're going to mix the two together, and it's going to, kind of gel together to form a little bit more of a solid, especially after it dries out. It'll form into a solid soap. Okay? And the soap will look like this. And I'll explain how soap works. Soap looks like that. All right? You also get reformed glycerol, too. There's a little bit of glycerol that's going to be formed as well. But this is going to be your soap. What you've done here is, let's watch. What you've done is this RC-O1OO used to be RC-O1OO. We used to be connected to this guy, right? Well, we split him off. And instead, the Na is on the end of every one of these. And that means that I've got a very, very polar area here. It's charged. Okay, it's charged. It's not even polar. It's actually charged. A real full charge on it. And then I got over here, this R group. Remember, he's 17 or 20 carbons long. He's very nonpolar. Why is that useful? To have a single molecule that has a very strong charged area and a very good nonpolar area. Well, then let's think about what our rule about solubility. What's the rule about solubility? Like dissolves like. So soap is a great guy. you could dissolve, soap will dissolve polar and nonpolar things, because he's got both there. The larger this R portion, as a matter of fact, the better it's going to dissolve those stains, the dirt, the grass stains. Okay? I mean, if I get grease on my hands and I just have water and no soap around, very difficult to wash that off. If I'm working on the car and I only have water, I can't wash that off. Okay? I can wash it off very well with gasoline. It'll wash that grease in the car off. But I don't want to wash my hands with gasoline. I don't want to wash my hands with turpentine. They're going to smell, and it's carcinogenic anyway. You shouldn't do that. So we use soap. Soap's got a non-polar part to wash away the grease, but it's also got a polar part, so it will dissolve in the water and run down the sink. That's how it works. Let me show you a little demo I did for you last year. I took some water. Turn that light on for a second. I took some water, and I added some oil to it. And this is when I was trying to illustrate for you guys the concept of like dissolves like. Put a little oil in there. That's a little too much. Okay, I put a little oil in there, and I got 2 layers. Clearly I have 2 layers. You can see the 2 layers. That's actually a bubble down below. All right? If I shake these guys up, okay, you'll find in just a very short period of time, there's no soap in there to begin with, this guy's going to separate back out into the oil and the water. Wash my hands off a little bit. There it is. So if I look at him again, he is separating back out into the oil and the water. Okay, this is clearing up at the bottom, and it's getting a layer of oil at the top right away. We know this happens with our oil and vinegar salad dressing. Oil is very non-polar. Not a lot of charges in oil. Water is very polar. They don't mix. They separate back out. You've all seen salad dressing do this. But if you want to keep your salad dressing together, just add a little soap to it before you put it on your salad. Don't really. But if I add a little soap to it, all right, and I shake it up, all right, I'll notice that it won't separate out as well. It'll actually stay together. I also use this to talk about solution suspensions and colloids. Okay? Now you say, well, I see 2 layers. There's this layer up here. What is that layer up there? That's just foam. That's just foam. All right. So if I look at this guy, and if I look at him a little later from now, he will stay like that. At least he'll stay like that better than he would if I just shake up water and oil. You know, obviously, turn the light off. Obviously, we don't want to add soap to our salad dressing. But what can we? Why don't I want to add soap to my salad dressing? Because it's going to make you sick. Soap doesn't taste very good, and it's probably not very good for you to eat it. However, what can I add? What do I add to make a different kind of salad dressing that will do the same thing? Keep them from separating out.
Mayonnaise.
Right, that's how you make mayonnaise, like in French or Thousand Island or ranch. They use mayonnaise. How is mayonnaise made? It's just oil and vinegar. Just like the regular oil and vinegar salad dressing. But it doesn't separate out because it has what else added to it? Egg whites, exactly. See, egg whites do the same thing soap does. They act as an emulsifier. They keep these guys from separating out, just like soap does. Difference is, I can eat egg whites. I can't eat soap. Okay, and that's why we use it. I mean, you can eat soap if you really, really want to. You'll get sick. I wouldn't recommend it. Of course, some of you probably had your mouths washed out with soap when you were kids. I don't know. Like in that movie. So, it's so poisoning. Yes, exactly. So poisoning. All right. So you got the idea. This polar portion right here. Okay. That charged portion. That guy dissolves in the water. This guy dissolves in the stain. Because most of the stuff we get on our hands, food stains, grass stains, dirt. It's organic. It's non-polar. Okay. There are a few things that are charged. Sugar. If I'm eating a lollipop, my hands are sticky. I can wash it off with just plain old water. It washes right off. Why? Because sugar dissolves in water. All right? But most things don't do that. Most of the stains we get on our clothes, most of the stuff we get on our hands are organic stains, and they wash off better with soap. All right? And that's what we're going to make on Thursday. Okay. Now I need to shut this off while we do one more thing.